Hello and welcome to our talk as part of the stay-at-home edition of RuhrSec 2020. Today we are going to talk about our analysis of cognitive factors in order to impede hardware reverse engineering, or as we coined it, our roadmap to cognitive obfuscation. If you would like to know what exactly that means, please watch the following talk. In order to holistically explore the processes in hardware reverse engineering, we set up an interdisciplinary research team made up of a psychology squad consisting of my colleague Carina Wiesen and her supervisor Nicole Rummel, and a security squad comprised of my supervisor Christoph Paar and myself. Together, we are a part of the SEC Human Research School at Ruhr University, which covers a broad range of security topics from different societal and technical perspectives. First, let's get started with some background. What is hardware reverse engineering, and why is it interesting for both security researchers and cognitive psychologists? When we develop a new product, we usually start with a high-level description. Building the product from its description is called engineering. Now, if we want to go into the opposite direction, from a finished product to its high-level description, we apply reverse engineering. When dealing with hardware, reverse engineering can be applied for a variety of legitimate and illegitimate purposes. Legitimate applications encompass competitors' analyses, such as the detection of counterfeits or the confirmation of IP infringements. More recently, the search for malicious circuit manipulations has become an important application. At the same time, hardware reverse engineering can also be used for the opposing illegitimate purposes, such as design plagiarism, IP infringement, or the implementation of hardware trojans. So how does hardware reverse engineering work? In the case of integrated circuits, first the die has to be removed from its package. Depending on the specifics of the carrier material, different techniques have to be used. Those range from the application of strong chemicals over mechanical abrasions and heat treatments up to decapsulation with a laser. After decapsulation, the die has to be delayered via different forms of etching. Every layer is then imaged with a scanning electron microscope before those images are stitched together and corrected for errors in the image processing step. After further annotation and recognition of standard cells, a flat logic netlist can be extracted, which has to be analyzed subsequently. While the steps required for netlist creation are generally well understood, the step of netlist analysis marks the core of our investigation. Similarly to ICs, netlists can be extracted from field programmable gate arrays. First, the bit stream has to be accessed and possibly decrypted, which both has been shown to be possible in several prior works. Next, a reverse engineer has to analyze the file format in order to transform the bit stream into its gate-level netlist description. The analysis of FPGA netlists follows the same basic principles than the analysis of IC netlists. Let's take a closer look at netlist analysis. While one might think we will receive a netlist nicely grouped by its functional blocks, as depicted here, well, what we actually get looks more like an unstructured chaos of gates and their interconnections. Keep in mind that the analysts have no variable names or such, which could aid their analysis. In order to enable the initial netlist analysis, the netlist can be interpreted as a graph. In this graph, gates can be seen as nodes, while their interconnections serve as edges. Now, when initially exploring the netlist, the analyst can employ already existing or custom-developed algorithms from graph theory in order to identify certain functional modules based on their structural characteristics. A common example for structures, which can be detected via existing algorithms from graph theory, are control modules such as finite state machines. After initial modularization, the modules of interest have to be inspected further, also incorporating their basic combinational functionality and sequential behavior. Depending on the goal of the analyst, not the entire netlist has to be reversed, but it may be sufficient to only analyze the areas of interest. For example, a reverse engineer who wants to extract a hard-coded key from an AES core might first search for the unique structure of the S boxes in order to conduct malicious manipulations on them, which eventually lead to key extraction. In summary, the processes of hardware reverse engineering can be extremely time-consuming. This is even more so since no fully automated tools for hardware reverse engineering are available, and human analysts are forced to combine several complex semi-automated steps in the sense-making process. Based on this background, we derived the following model for hardware reverse engineering, consisting of several automatable steps which have to be manually combined by a human analyst. Following the technical literature, we implicitly assume that netlist reverse engineering contains 3 consecutive phases. In the first phase, the analyst identifies the components of interest, often through structural means. In phase 2, those candidates are further examined and verified in order to proceed with phase 3, which encompasses the realization of the analyst's goal. So far, we took a predominantly technical look on hardware reverse engineering. However, our understanding of hardware reverse engineering also includes manual actions by human analysts, since no fully automated tools exist. In order to develop novel countermeasures, we first have to understand the cognitive processes mainly influencing the success of hardware reverse engineering, which will be explained by my colleague Carina Wiesen.
As defined in our model, cognitive processes of the human reverse engineer are always involved in hardware reverse engineering. This means that those cognitive processes mainly influence the success of hardware reverse engineering, but are surprisingly poorly understood so far. In the following, we give an overview about the little number of prior research and derive our research gap in questions. One relevant prior work is the research conducted by Lee Johnson-Laird, who defined a theoretical model of reverse engineering of Boolean systems. But first of all, we start with the quotation, which says that reverse engineering of Boolean functions is seen as a special sort of problem solving. What do psychologists mean by problem solving? From a psychological perspective, problem solving has always a purpose, meaning that a problem solver tries to achieve a desired goal without knowing how to achieve it. The problem-solving process is not totally reliant on automatic processes, meaning that the problem solver has to develop a strategy based on controlled processes. Additionally, the problem solver lacks in skills and knowledge how to produce an immediate solution. In general, the beginning of a problem-solving setting, the problem solver is confronted with the problem, meaning he or she is in an initial state. The desired solution is in the future, is defined as the goal state. In the initial state, it is not apparent to the problem solver how to close the gap between initial and goal state. But what does a problem-solving scenario look like in hardware reverse engineering? The problem solver gets the netlist of an unknown chip design, what we would define as the initial state. His or her goal is to find relevant candidates from that netlist. For that, he or she applies a multi-step process. The problem solver selects actions and operators, like problem-solving strategies, to transform the initial state into the goal state. The problem solver uses prior domain-specific knowledge to change those states, to make decisions, or to manipulate information. Moreover, the problem solver acquires skills and domain-specific knowledge, which he or she applies in the selection of actions and operators. Coming back to Lee Johnson-Laird, who defined reverse engineering as a specific type of problem solving. Therefore, the authors conducted 5 experiments with students from 2 universities. Students did not have strong backgrounds in relevant topics like electrical engineering or cybersecurity. During those 5 experiments, participants were asked to draw electrical circuits based on a Boolean algebra. In the figure, you can see the example of an AND problem. Both switches have to be activated in order to turn a light on. The participants had to draw a specific circuit representing the lightning problem. Lee and Johnson-Laird conducted their research in a laboratory setting and measured solution time and solution correctness, and also conducted interviews. Based on their experiments, the authors derived the following results. 3 factors are influencing the difficulty of a reverse engineering problem. The first factor is the number of components. The second factor is the number of settings influencing an output, meaning the component settings. The third factor are the dependencies on components on one another in influencing an output. Secondly, the 2 main strategies were that the problem solvers rely on an initial strategy in solving the problem settings of either focusing on the outputs one by one or on the components of the systems one by one. We evaluate the theoretical model by Lee and Johnson-Laird as an important step to shed light on underlying cognitive processes in reverse engineering. Nevertheless, it is unclear to what extent the results are valid for problem-solving processes in the domain of hardware reverse engineering. This is based on 2 main aspects. In hardware reverse engineering, there's a more complex problem-solving setting. Remember the Netlist visualization in the beginning. Furthermore, important influences of individual preconditions like the level of expertise or prior domain-specific knowledge might be thinkable factors which influence the problem-solving processes in hardware reverse engineering as well, but which were not studied in Lee and Johnson-Laird's experiments. Based on this evaluation, we derive the following research approach. We adopt the definition of cognitive processes being problem-solving processes for the hardware reverse engineering domain. We conduct experimentary studies with hardware reverse engineers who solve a realistic problem-solving task. We observe and analyze their behavior by considering also influences of prior domain-specific knowledge and cognitive abilities. This leads us to the following research questions. In order to shed more light on the underlying technical and cognitive processes of hardware reverse engineering, we derive the following research questions. First, can the phases of human sense-making be detected during the hardware reverse engineering processes? And if so, which are the crucial ones? Which strategies distinguish more and less efficient reverse engineers? And which cognitive preconditions play a role for the success of hardware reverse engineering? How can those insights be used to derive hypotheses for cognitive obfuscation? In order to answer those questions, we conducted an exploratory study. Please note that this exploratory study and the results are under submission. On this slide, you can see how the exploratory study was conducted. Within 2 weeks, we recruited graduate and undergraduate students with relevant backgrounds in cybersecurity. Over a period of 14 weeks, they acquired skills and knowledge in hardware reverse engineering. In 4 hardware reverse engineering tasks, they practiced different problem-solving settings. After the training phase, they had to solve a realistic hardware reverse engineering problem within 2 weeks. From this sample, 8 excellent top-level students were excluded based on their solution probabilities. In the final phase of the study, we were able to recruit 1 hardware reverse engineering expert who solved the same hardware reverse engineering problem task. Please note that all participants provided written informed consent and received a monetary compensation. Privacy was realized by randomly assigned pseudonyms, which were consistently used during the whole study instead of the participant's clear name. During the study, we collected several variables. As dependent variables, we measured total solution time, time spent per phase, and the number of manual and automated netlist interactions. Those dependent variables were extracted from automatically recorded log files from working with our hardware reverse engineering tool HAL. Furthermore, we collected cognitive abilities with 3 tests, including perceptual reasoning, working memory, and processing speed. And we collected control variables like age, the major or the target degree.
The idea of a hardware watermark is to hide unique information in the netlist which is not related to its functionality and can easily be read out by the intellectual property owner. With this method, IP owners can lead the proof of authorship when the netlist was cloned for plagiarism. The watermarking scheme used in the study task hides signature bits in unused parts of lookup tables. In the study task, the participants found themselves in the realistic setting of a white hat hacker receiving a netlist containing the described blood-based watermark. The underlying design was a real-world encryption core. Their objective was to clone the design without copying the watermark, therefore effectively removing the watermark protection from the circuit. All participants solved the study task with the realistic hardware reverse engineering environment HAL, which is publicly available under MIT license on GitHub. The hardware analyzer HAL is a sophisticated tool enabling the graphical representation and interactive analysis of gate-level netlists. Among many other features, it allows for visual inspection of netlist and its elements on the one side, and has an integrated Python shell to exploratively interact with the netlist on the other side. Most importantly for our study, HAL enables behavioral analysis of the participants solving the study task. Therefore, it allows us to understand and explain their behavior. In the following, we will present a selection of our results regarding research questions 1, 3, and 4. Let's briefly recall our face model and define its meaning in the context of the study task. In phase 1, analysts identify components of interest. In our study task, they had to identify all 50 components which potentially implement the watermark in order to finish this phase. In the second phase, those candidates have to be verified, and therefore the analysts had to extract the actual watermark message from the candidates. In the last phase, participants had to remove all watermark messages in order to clone the underlying design. In research question 1, we were interested if those phases could be detected during the hardware reverse engineering processes of our participants, and if yes, which phases would be the crucial ones. As shown in this figure, all participants, including the expert, progressed through the assumed phase model with a total solution time between 3 and 6.5 hours. While absolute and relative solution times moderately differed between participants, phase 2 took a total of 58% or 2.5 hours of participants' time on task, and marks therefore the core of the analyst's investigation. Last not least, most manual analyses of netlist components took place in phase 1, while script-based analyses predominated in phases 2 and 3. Next, we would like to present one interesting finding with regard to research question 3, where we investigated the cognitive factors playing a role for the success of hardware reverse engineering. The descriptive data shows that participants with higher scores in working memory tend to solve the task quicker than participants with lower working memory scores. There appears to be one outlier in the data, which is discussed in our paper. We want to highlight the descriptive nature of this finding, since the small sample size rendered statistical analyses of the influences of cognitive factors impossible. Nonetheless, we think this finding serves as the basis for future research and should be understood as a first implication of the working memory as a factor which might influence performance in hardware reverse engineering. After briefly presenting a selection of our results, I would like to zoom out a little bit. In our study, we monitored the behavior of reverse engineers performing a realistic task. In order to approach the overall objective of our research, which is to make hardware reverse engineering as difficult as possible on both the technical and the cognitive side, we first need to better understand the processes of hardware reverse engineering. And second, we need to harden against those hardware reverse engineering processes. This second step is what we call cognitive obfuscation. In current literature, there exist several strains of hardware obfuscation. What unites them is that they are all solely based on technical approaches and that they lack common evaluation criteria. We argue that hardware reverse engineering always involves human analysts who manually combine several semi-automated techniques. Therefore, we need to define metrics which incorporate the cognitive processes in order to evaluate existing obfuscation methods and ultimately create novel obfuscation based on those insights. But what is obfuscation at all? Here's an analogy. In this picture, you can see a neatly organized power pole. Imagine you want to find out which of your neighbors is connected to which line. This looks like a manageable task, doesn't it? This is our netlist without obfuscation. Now take a look on the right side and imagine the very same task. Looks a lot harder, right? This is our obfuscated netlist. Let's recall our graph from the beginning. We assume that the engineering part from the high-level description to the finished product is, well, easy, while the reverse engineering part is not that easy. Now, if we introduce obfuscation during engineering, the engineering part should still be moderately easy, while the reverse engineering part is supposed to become insanely difficult. With respect to our fourth research question, which aims to derive first hypotheses for cognitive obfuscation, one of our suggestions is to compose netlists where obfuscated components are hidden in one or several of many equally looking regular structures. In order to create those structures, obfuscation primitives such as dummy wires and camouflaged gates can be used. This would result in a larger set of candidates returned as a result from phase 1, therefore significantly slowing down phase 2, where all those candidates have to be inspected in detail. Another path we want to follow in the future is to overload the capacity of the reverse engineer's working memory by the development of structures which force the analyst to apply a combination of many different strategies simultaneously. In summary, our work marks a first step towards a better understanding of technical and cognitive processes in hardware reverse engineering. In the behavioral data of our participants, we could detect a model of 3 consecutive phases. We also analyzed the interactions of manual and automated netlist analyses, which was not part of this talk. Last not least, we identified the cognitive factor working memory as potential catalyst for hardware reverse engineers. Indeed, our work comes with a number of limitations. One of them being our sample size of students, which did not allow us to conduct any statistical analyses. Further, we developed our model based on the analysis of a single medium complex task, and it remains unclear whether the results transfer to different settings. More complex real-world tasks could potentially lead to an extension of the model. Based on this work, we will continue to work on our novel class of countermeasures against hardware reverse engineering, which we call cognitive obfuscation. One important aspect on this path will be the quantification of cognitive influences on the success of hardware reverse engineering. This marks the end of our talk, and I would like to thank you for watching our presentation. If you have any questions, please feel free to reach out to us via email.